We constantly guess what the future will look like, but we rarely ask how it will be funded. Let's run the numbers. Today, we analyze the critical hidden economics of artificial intelligence. As computing power becomes cheaper and more abundant, many analysts assume that advanced models could grow without limits. Yet, a severe physical constraint is silently emerging behind the scenes of this industry. This binding constraint is not processing hardware or electrical energy, but high-quality training data. The economic landscape of artificial intelligence is rapidly pivoting from compute abundance to an extreme informational resource scarcity. To train increasingly capable systems, developers require massive streams of structured human information. However, the readily available public data on the open internet is already nearing total exhaustion in several key domains. When artificial systems attempt to train on their own synthetic outputs, they often suffer from model collapse. This recursive loop degrades the overall cognitive quality of the resulting neural network over time. This situation creates a fundamental economic puzzle. Why could premium data remain scarce and expensive even as the artificial intelligence models themselves become incredibly capable, cheap, and accessible to the whole world? Let us examine the problem. In any industrial production system, the cheapest inputs are substituted for the most expensive inputs until a new cost equilibrium is finally reached by the system developers. Now, compute is the cheap input, while human-curated data represents the expensive bottleneck. This complex economic asymmetry alters how capital and resource allocations are distributed across the technology sector in this scenario. If a developer cannot buy more high-quality information, adding more processors yields rapidly diminishing returns. The marginal utility of compute falls sharply without the constant presence of novel and structured training inputs. This scenario implies that the value of the final system is determined not by raw processing power, but by exclusive access to scarce information reserves that cannot be replicated by competitor firms. Consequently, the owners of proprietary data repositories hold immense market leverage. They can demand high rents from technology companies that require these historical and structured archives to perform their model training runs. This shifting balance of power changes the general economics of technology development. It comes down to scarcity, where the scarcest economic asset captures the majority of the final financial surplus generated here. To understand this deep dive, we must define what makes information valuable. Information theory suggests that learning requires novel entropy, which is defined as surprise or highly unpredictable and complex structural relationships. Repetitive or synthetic data lacks this critical entropy, meaning it fails to teach the model new relationships. It merely reinforces what the artificial system has already acquired during its previous training phases. Therefore, high-quality data is not just any text, but a structured representation of real-world complexity, physical laws, human reasoning, and rare edge cases that are exceedingly difficult to simulate and predict accurately. This complex representation is generated through real-world friction and genuine human experience. It cannot be easily synthesized by an algorithm that only understands patterns within the information it has already ingested before. Because of this, we must distinguish between processing capacity and informational richness. One is a rapidly replicating manufacturing commodity, while the other is a strictly finite and currently non-reproducible global natural resource. As this resource is depleted, the economic cost to extract the next unit of valuable information increases. Developers must look away from the public web and toward highly specialized expert data archives. This search introduces a difficult coordination problem. Unlike physical commodities, informational quality is hard to verify before purchase, which complicates transactions between buyers and sellers in this specific and highly fragmented market. This asymmetric information creates a classic lemons market. Buyers fear purchasing low-quality or synthetic data, leading to transaction failures and significantly higher search costs for developers operating across the artificial intelligence industry. Let us trace the core mechanism of this transition. When compute is cheap and abundant, demand for training inputs rises dramatically, driving up the global market price of verified human archives everywhere. This price signal incentivizes organizations to protect their private repositories. Public websites that once allowed free web scraping now erect strict paywalls and license agreements to monetize their private data assets. As a result, the internet becomes highly fragmented. Information that was once treated as a public good is enclosed into private assets, transforming the open web into a network of digital fiefdoms. This enclosure process redistributes economic surplus from model builders to proprietary archive owners. The returns on building algorithms decline, while the returns on holding unique and clean information assets tend to grow. Interestingly, this mechanism suggests that the competitive advantage in artificial intelligence may lie not in engineering talent, but in the historic possession of massive and highly exclusive information silos under this scenario. Under this mechanism, small developers who lack significant capital are locked out of the market. They cannot afford the licensing fees required to train highly competitive networks, limiting the overall industry diversity. This creates a high barrier to entry, consolidating the developer market into a few wealthy conglomerates. The initial promise of a highly decentralized algorithm development faces a harsh physical resource constraint here. Furthermore, the scramble for human archives leads to defensive information generation. Technology firms might hire thousands of human experts to write highly unique text, translating digital engineering back into physical human labor. This translation shows that intelligence scaling remains deeply anchored to human cognitive output. We may not easily bypass this human bottleneck by simply adding more processing layers of compute to our existing model architectures. The economic incentive to capture human experience becomes the primary driver of these new platform designs. Follow the incentive structure to determine which business organizations can survive the next development wave here. This dynamic shifts capital from hardware factories to institutional archives, including hospitals, law firms, and scientific publishers. Under this assumption, these institutions could become the key new gatekeepers of global technological progress. However, this allocation of resources creates structural inefficiencies. Capital is spent acquiring existing information rather than developing new capabilities or building better computing infrastructure to support our global society's complex real-world development. As rent-seeking behavior intensifies, the cost of training next-generation systems may rise faster than the efficiency gains of the new hardware, slowing down the overall pace of technological innovation in this scenario. Consequently, the industry might reach a plateau where the cost of acquiring the next increment of data exceeds the marginal revenue that the highly improved model generates for its developers in practice. This plateau would force a redesign of the industry's business models, shifting focus from general cognitive intelligence to narrow and highly specialized applications that require far less training information under this scenario. To validate this speculative economic thesis, we must consider the key boundary cases. For instance, what if synthetic data generation is more successful than current theory suggests under our baseline assumptions here? Under a scenario where models learn to self-correct through logical rules, the overall demand for human data could decline, lowering the transaction fees and licensing rents for participants in this technology marketplace. However, this alternative equilibrium assumes that logical consistency is a complete and perfect substitute for empirical discovery, which may not hold true in highly complex, unpredictable, and dynamic real-world environments over time. Another limitation is that a different algorithmic architecture could emerge that generalizes from very few training examples, much like the human brain does, thereby bypassing this current massive training data bottleneck. Under this alternative assumption, the economic value of massive historical archives would collapse, shifting all market leverage back to the designers of new learning algorithms and these highly specialized hardware processing systems. We must also analyze the case of specialized domains. In chemistry, models can run physical laboratory experiments to generate their own high-quality training information, bypassing human archives and the public web data. Yet, this validation is restricted to physical sciences where simulator rules are precise, leaving human social, cultural, and linguistic information as the primary and remaining scarce economic bottleneck for advanced machine intelligence. Let us resolve the opening economic mystery. Why does premium data remain scarce when these artificial systems are highly capable? It is because synthetic generation would tend not to create new and raw primary experiences. An artificial model can interpolate within its existing training distribution, but it may not easily extrapolate to capture novel real-world occurrences that have not yet transpired in this complex physical universe here. Under this assumption, the real world remains a primary generator of true information entropy. Numerous new human interactions, scientific discoveries, and societal shifts produce highly unique and valuable data for training runs. Therefore, compute would tend not to replace the raw material of experience. The abundance of processors simply increases the velocity at which developers consume the finite resource of reality to train models. This realization changes the economic definition of technological wealth. It is not the direct capacity to process existing information, but the capacity to capture live, unrecorded activities from our active real world. As a consequence, the economic rent of the digital economy shifts outward, away from silicon chips and toward these physical interfaces that record human behaviors and real-world interactions in this scenario. This explains why technology conglomerates are expanding into physical retail, healthcare, and smart consumer home devices. These are not diverse businesses, but proprietary and highly structured active data harvesting operations in practice. They are securing these vital informational input pipelines before the digital well runs dry, ensuring they can feed the massive compute infrastructure that they have built over the past several calendar years. The economic resolution is clear. Compute is a commodity, while genuine experience is a scarce resource. The final value lies in the interaction, not the calculation of existing information in this scenario. The funding model decides what survives. Investors who finance massive chip hardware factories without securing unique training data pipelines may face declining capital returns in this speculative technology scenario. For developers, the implication is practical. Instead of attempting to build larger neural networks, their focus should shift to designing better incentives for human data contributors in this market. This might involve complex micropayment systems or shared equity designs, where contributing individuals are compensated for the unique informational value they add to the collective artificial intelligence model here. Without these institutional innovations, the supply of high-quality training inputs could contract, slowing down the deployment of advanced and highly capable systems across several sectors of our global economy. Furthermore, national policymakers must reevaluate information ownership laws. If unique data is the key economic input, its societal distribution determines the relative economic wealth of nations going forward. A centralized data repository owned by a single dominant conglomerate could lead to extreme monopoly power, stifling competitive innovation and reducing overall consumer welfare in this speculative market scenario. Conversely, a decentralized public data trust could foster open and collaborative innovation, allowing smaller development firms to compete effectively on a level playing field with these larger corporate conglomerates. Ultimately, the path we choose depends on how we frame the value of unique human contribution in an increasingly automated, digitized, and highly complex global digital information economy. When compute becomes highly abundant, the primary asset that holds true economic value is the non-replicable signature of real-world friction. The future is just incentives at scale. See you tomorrow.